Welcome back to the Python for Beginners series. We have encountered string data objects many times in previous works. We learned how to create them, use them as a data source for other objects, and explained their basic properties. In this episode, we will show other options for working with the string data object and, above all, how to format it so that it is readable even by ordinary people. We will also learn how to create our own functions, and in connection with this I will also show you Lambda expressions, which in some cases can replace simple functions. So far, we've learned how to create a string object by simply writing a few characters enclosed in apostrophes or quotation marks. We also learned how to create a multi-line string, which must be enclosed in triple apostrophes. Everything between the opening and closing apostrophes is the content of the string. Python allows you to create an object of type string also using special literals, which we will also show in the examples. By specifying a special literal, we can create binary, raw, Unicode, and formatted strings. Let's review knowledge and learn something new. We already know the standard way to create a string object. We have always enclosed the text in apostrophes or quotation marks. Let's focus on the T2 object we just created. If we pass it as a parameter to the print function, nothing special happens. The contents of the object will appear exactly as we entered them on two lines. But when we ask the interpreter directly about the contents of the object, the text is not only displayed on one line, but also two characters that we did not enter appear in the middle. These characters are called escape sequences. It is a sequence of characters that always starts with a backslash character and is followed by the meaning part of the sequence. Python, like other programming languages, knows several such sequences and every programmer should know them. The table contains a brief overview of them. Some of them we will meet very often, others we will use very rarely. But it is good to know about them, so that they do not surprise us, for example, when studying the code of other programmers. These escape sequences are very often used. They insert characters for a new line or a tab. However, escape sequences for inserting apostrophes and quotation marks are important. Now we'll show you why. Imagine you want to print the sentence "Father's house is small." The entire text must be enclosed in apostrophes. The problem is, however, that there is another apostrophe inside the sentence. The interpreter of the language therefore rightly considers it the end of the text. But other characters are inserted after this end, and one word is even a Python operator. Therefore, quite logically, an error will occur. In order to use an apostrophe inside a string, we have two options. Either we enclose the entire string with quotation marks, or we use the escape sequence of the apostrophe character. We can try even more sequences. As you can see, the interpreter inserts tab characters between the numbers. The backspace sequence works just as well. However, the Python language has many more options for creating an object of type string. If we write the special combination of characters we talked about a moment ago before the first apostrophe, the interpreter will treat the string somewhat differently. Let's show all the options, but by far the most used is the F string. Since the interpretation of this type will be the most comprehensive, we will discuss it at the end. The first prefix that can be written before a string literal is B. If we write a lowercase or uppercase letter B before the initial apostrophe, Python will treat such a string as binary. In practice, this means that any character of the ASCII table can be written into the string. This means any 1-byte character encoded with the digits 0 to 255. The second possible prefix is R. If we write it before the opening apostrophe, we tell the interpreter that we are going to enter a raw string. Such a string does not respect escape sequences and each character represents itself. It can be used perfectly, for example, if we need to work with paths to files that contain backslashes. Today, Unicode strings are used instead of binary strings. We create such a string by writing the letter U before the opening character of the apostrophe. We can then write any 2-byte coded characters into the object. the most used prefix is the letter F. If we enter it before the opening apostrophe, we tell the interpreter that we will enter a formatted string. Strings can also be formatted using the string objects format method, but using F strings is more elegant and nowadays more preferred. We will show it with examples. Expressions can be used in F strings. The expression part of the F string is enclosed in curly brackets. These expressions are then evaluated when the object is created and the result is inserted into a string. A huge advantage is the fact that there is no need to check the data types of the objects we insert into F strings. The interpreter will do it for us. The evaluation is performed only once. This means that if the value of the embedded object changes, the value of the F string will remain unchanged. We can perform calculations in the expression, or use any built-in function. We can just as well call any method of any existing object. If we need to format numbers, Python offers several options. The first and by far the most used is to round a float number to the number of decimal places. By writing this expression, we tell the interpreter that we want to mathematically round the number to 2 decimal places. F stands for fixed. If we need to, we can nest the expressions arbitrarily. For example, we can insert the formatting expression itself. Python always evaluates it from the inner expressions towards the outer. This means that it replaces the precision variable first before evaluating the pi variable. Let's look at other formatting options for which we define a few numbers. In simple division, the interpreter writes the number in a special form. The number is so small that the interpreter wrote it in exponential form so that we don't have to count how many zeros are after the decimal point. This expression means that the result of the division is the number 2.35 times 10 raised to the power of -5. If we format the number to a fixed 10 decimal digits, we can see what this expression actually means. Trimming to 2 decimal places gives us the number 0 with the 2 decimal places we want. The number can also be expressed as a percentage. In our case, we require 6 decimal places. Whole numbers can be expressed in a simple way in the octal and hexadecimal system or in exponential form. Here as we see, a million is 1 times 10 raised to the power of 6. We expect other options for strings. It is primarily about string alignment. In this way, we can align the string on the right, with the necessary number of spaces added to the left, to the desired length. We can do the same with a number. The interpreter has no problem with this, it converts the number to a string and aligns it. We can even use a combination of formatting expressions as a masterpiece. Here's an expression that first converts to 2 decimal numbers and then right aligns to 10 characters. At the end, we can practice loops and write out a table of multiplication of small numbers. I used one new procedure. I passed the end parameter to the print function and its value is an empty string. The end parameter of the print function indicates which characters should be used to end the output of the function. By default, the function uses the new line character. But we told the function that we don't want a new line character at the end of the output, but that we want to continue with the next output on the same line. Therefore, I used an empty print function at the end of the while loop, which does not print any data, but only shifts the output to a new line. We have shown how to call functions many times. So far we've been using built-in functions exclusively, and now it's time to learn how to write your own functions. We can then use them in our programs in the same way as we use the built-in ones. Since we've known for a long time that everything is an object in Python, it's no surprise that functions are objects too. Creating them is easy. The def keyword is followed by the name of the function, followed by parentheses containing the list of parameters, and since it is a block statement, followed by a colon. We can call this line the header of the function. Before the final colon, the type of the data object that the function returns in the return value can optionally be specified. we call it annotations. This notation is not required by the interpreter, but it will help the programmer in better orientation in the code. The body of the function follows, which is a sequence of statements that are appropriately indented, as we already know with block statements. The function body must not be empty. This rule is based on the Python language definition. Therefore, we can often encounter the pass statement, which is the only statement in the body of a function. The command does nothing at all. Such notation simply defines an empty function that the programmer can add later. I'll show you how else to make great use of an empty function later in advanced functions. Each function returns a value. If we specify a return statement followed by an arbitrary expression, the return value will be the result of that expression. The return statement is optional. If we don't specify it, the function will execute and return none when called. Before we show examples of how to use the functions, let's say a few more notes on terminology. If we define a function that receives some values on input, we usually do it by writing similar code. In order to be able to distinguish the meaning of the variables that are passed to the function and which are processed by the function in the following explanation, let's remember the following terms. An argument is an expression with which we pass the function the data we want to process. In contrast, a parameter is a variable that the function itself works with. This designation is important so that we know what variables or objects we will talk about in connection with the work of the function. If we pass arguments to a function, we pass it already existing and initialized objects. On the contrary, the parameters are initialized by the function itself automatically as soon as it is called. The expression that follows the return statement is called the return value. We can say that the return value is the result of the operation of the function. All variables that we define inside the function body are local. This means that their life ends when the function body is executed and the return value is sent. We explained what functions are and how their construction looks like. Now we can see how to use them in practice. If we remember the mathematics lessons at school, we certainly have one formula for the decomposition of the power of two numbers. We will borrow one part and do some experiments with it. For the numbers a and b, which are 2 and 3, we can simply write the print command. But the problem arises when we need to change the numbers a and b. Then we use variables. We can already do that. But then it may happen that we need to use the expression several times. For example, to evaluate the condition. Not only is such code not pretty, but there is a high probability that we will make a mistake when writing it. Therefore, it is more advantageous to define a function that will always perform an identical calculation based on the parameters we pass to it. We only check the formula in one place in the code, and then we don't have to worry about making a mistake somewhere. The code is much more readable and clear. When working with strings, we used to show the notation of a string enclosed in 3 apostrophes. I promised we'd come back to this topic. Now is the right time. If we define any function, we can write its documentation comment in just this way. If we write it in a function defined by us, we can then call up its help. Writing documentation comments is part of every programmer's good manners. Of course, you don't need to describe everything, but if another programmer gets his hands on your programs after a while, he will certainly appreciate that the functions are documented. It saves a lot of work in code study. After all, as you can see, even the basic building blocks of the Python language are documented and will provide you with a lot of useful help when writing. So far, we have only shown the basic use of custom functions. The function receives a known number of parameters and performs the calculation. Because programmers are lazy by nature, they often want to save themselves the work. Therefore, there is a way in Python to ensure that some parameters do not have to be passed to the function. We could have noticed this possibility a while ago with the print function. Let's look at her help. The end parameter can be passed to the print function. But if we don't pass it, we see in the function definition that it has a default value. This value is the new line character. We can do the same in our functions. We define a completely simple function. The function correctly calculates the square and third powers of 2. But if we don't specify the second parameter, the default value is used. If we don't pass any parameter, the function will of course end with an error. We can define functions where the order of the parameters does not matter. Such a function might be a simple calculation that multiplies two numbers. If we swap the arguments, the result will be the same. But the second function is different. Here, the order of the parameters matters. Parameters passed in this way are called positional. This means that when passing arguments, their order matters. When using them, the programmer has to remember what argument and at what place he must pass the function in order for the result to be satisfactory. But Python also allows the use of named arguments, as we saw with the print function. Let's remember that the print function can receive any number of arguments. It will print them all one by one. But since the function does not know in advance how many parameters it will receive, it must use named parameters in addition to positional parameters. These are named arguments. With these arguments, we can tell the print function which characters to use to separate the individual positional parameters and what to print at the end of the output. Let's try to improve our function. We will not return the value of C, but we will print it directly in the function. We will print it as many times as we specify in the n argument. If we call the function without the n argument, the function will use the default value of 1. We can now call the function with positional parameters. There is nothing unusual about that. The function determines the parameter names according to the order given in the definition. But we can just as well call the function with named parameters. When calling, we do not have to follow the order of the arguments if we name them. Positional and named parameters can be combined as desired. If we follow only one rule. Once we use the first named parameter, all subsequent parameters must be named. If we break this rule, the interpreter reports an error. But that's not all magic with parameters. Python even allows you to force how arguments can be passed to a function. Therefore, Python introduces several notations for setting such rules. If we enter a /pseudoparameter in the function definition, we tell the interpreter that all parameters before the slash must be entered exclusively positionally. The parameters after the slash can then be entered as positional or named. Let's edit our function. With this notation, we tell Python that the arguments a and b can only be specified positionally and we must not name them. The function works correctly. The first two calls were made successfully. But as soon as we tried to name the arguments a and b, Python threw an error because we disabled it in the function definition. But what if we want to force parameters to be passed exclusively as named? For such a case, Python introduces another pseudoparameter, the asterisk. We will modify our function again. With this notation, we tell the interpreter that all parameters after an asterisk must be entered as named. A function call confirms this. If we name all the arguments, the function works correctly. If we name only the arguments b and n, the function will also run and return the expected result. If we don't name the b argument, the function call will end with an error. The asterisk and slash pseudoparameters can be combined without any problems, and this is often used in practice. If we modify the function to use both options, then we tell the interpreter that the a parameter must be specified exclusively in the first position, and the n parameter must be exclusively named. The function can then be called exclusively in these two ways. Any other call will cause an error. During programming, we very often encounter a situation where we do not know in advance how many arguments we will pass to a function. A typical function that has to deal with such a problem is again the print function. The function never knows how many objects we want to print, but it always prints all the objects we pass to it. Let's try it. We pass 3 and then 6 arguments to the function, and the function did not protest and always printed the correct number of passed parameters. In order for a function to effectively perform such a task, Python introduced a definition that we will encounter almost every step of the way. Let's try it on the new function. The function has 2 strange parameters. The first parameter says that all positional parameters will be stored in the positional object. It doesn't matter how many there are. The second parameter says that all named parameters will be stored in the keyword object. Their number is also arbitrary. In our function, we will list the content of both objects, their types, and the content of the object to see how the mechanism works. We call the function with several positional and several named arguments. And what happened? The function in its definition took all the positional parameters and wrapped them in a tuple object. It also created a dictionary object from all the named parameters. These objects have been known to us for a long time, and we know how to work with them. If we know that we will call the function exclusively with positional arguments, we can define the function without a second parameter. As you can see, everything is working properly. But if we add named arguments, the function reports an error. In addition to functions, Python introduces one more, similar object. It is a Lambda expression. Lambda expressions and functions belong to the so-called callable objects. That is, one can run them, pass them data to process, and expect a return value. A Lambda expression is a simplified form of a function. There is only one rule for its use. The return value must be defined by a single expression. A Lambda expression definition is preceded by the keyword lambda followed by a list of parameters. It is followed by a colon followed by an expression to calculate the return value. We can use a Lambda expression anywhere the Python language accepts a callable object. Then the Lambda expression is called just like the function. If we only need to create a small, simple function that performs only one calculation that can be written in an expression, we can use a Lambda expression. In our example, you can see that the result is the same, but writing the code is much simpler and therefore clearer. In the function, we calculate the square of the sum of two numbers. We can just as well write it as an expression. An expression behaves similarly to a function. It can be called repeatedly, and passing parameters is no different than calling a function. But the writing is a little different. First, we create an object to refer to the Lambda expression. We then use the keyword to tell the interpreter that it is a Lambda expression. And we list the required arguments. After the colon is the calculation formula that the Lambda expression evaluates and uses for the return value. Lambda expressions can be more complex. Arbitrary functions can be used in them, both built-in and user-defined. But the rule always applies that the resulting formula must be a valid expression. No Python commands can be used inside. Let's show some more examples. We don't need to assign any variables to the Lambda expression, we can use it directly. Of course, only if we don't want to use it repeatedly. We enclose a separate Lambda expression in the first parenthesis, followed by the second parenthesis with the parameter with which we call the Lambda expression. Lambda expressions are indispensable helpers, for example when filtering data. If we have a list of data that we need to filter, we use a Lambda expression that returns a Boolean value. Using this value, we then tell the interpreter whether to include the given element in the filtered list. The returned object is of filter type and needs to be converted to a list object or similar. I will explain why later. Lambda expressions can be used just as successfully when mapping a list. The map function performs the exponentiation indicated by the Lambda expression for each element of the data list. The result is a map object, which we again need to convert to a list in order to print it. We will surely come across Lambda expressions many more times in different situations. They are an integral and widely used part of the Python language. A while ago we showed how to write custom user functions that are reusable in our projects. Let's look at a few options and ways to use built-in and user functions that will come in handy in programming. Because Python also treats functions as objects, it allows several practices that are uncommon or outright prohibited in other languages. Let's look at a few more possibilities that writing functions in Python offers us. The first mechanism, often used in other languages, is function overloading. Python does not allow function overloading as such, but it can override the function. Let's show it with an example. We have two built-in functions print and len. We already know how they work. But if we do the magic, we can tell Python that the built-in print function will behave like a len function from now on. We simply overwrite one object in memory with another object. Python will forget that there was a print object and call a len object instead. Then we are not surprised that the print function prints the number 3. This mechanism is both useful and dangerous at the same time. If we write our own functions, we can make great use of it to modify the behavior of the program. But if we overwrite the built-in objects in this way, there is no going back. The only option is to restart the kernel and let it load all the standard functions again. As you can see, after restarting the kernel, the function already behaves as standard. The second mechanism, unseen in other programming languages, that Python introduces is the way to create functions anywhere. A function definition can be written anywhere in the code where a statement is expected. Of course, also inside other functions. In our example, we nested function B in the body of function A. If we query the object type of function A after running the interpreter code, we get the correct answer. This is a function. But if we do the same for function B, the interpreter will throw an error because it doesn't know function B. Function B is visible only to function A. Function A can call it at any time, but the interpreter considers it private and will not make it accessible from other parts of the program, unless we want it ourselves. We will show such an example in a moment. Sometimes a situation arises when we know that we have to write some commands in the program, but we have not yet thought about which ones and what exactly they should do. We have already shown the pass command. In this case, Python allows you to also write the ellipsis object, or its alias, in the form of 3 dots. The language interpreter takes no action at such a location. However, writing one of these notations is necessary to meet the Python syntax requirements. For example, because the function body must not be empty. Since any function is an object in Python, they can easily be passed as parameters to other functions. Using a very simple example, let's demonstrate the possibilities that Python provides us. We have an output function. It requires 2 arguments: function and data. As soon as we pass an object of the built-in function len and an object of type string to the output function, it will return the length of the string. We don't have to pass only built-in functions. We can create any custom function we want. Even in this case, the output function works correctly. We can just as well generate our own functions based on the passed parameters. Let's create a simple function generator. Let's call it, for example, makeFunction. The generator contains one internal function. It takes one argument x. And now comes the magic. The inner function returns the expression x raised to the power of number. At the time the inner function is created, the value of the number object is known. Therefore, its value will be substituted. For a complete evaluation of the expression, we only need to know the value of x. And we know that x enters the internal function as a parameter. Finally, we return the just created internal function object from the generator. So what happens if we ask the makeFunction function to create the first function? Let's call the generator with argument 2. In the inner function, the number is replaced by the value of the parameter 2. The next line takes the definition of the inner function and returns it as the output of the makeFunction. This is then stored in a variable and the new function is ready to use. The same thing happens when we call the generator with parameters 3 and 4. Now we can test everything. We have created functions to calculate the second, third, and fourth powers. If we call all the functions with argument 5, we get the result of 25, 125 and 625 as we expected. We explained how to create inner functions and how to work with them. What if, on the other hand, we need to modify an existing function and modify its behavior? For such cases, Python has a very often used function decorator. Let's look at a very simple example to familiarize yourself with this useful tool. We have a simple function to print a number that is passed as a parameter. We also created a decorator function. It receives a single parameter called function. If we write this line before the print number function, we tell the interpreter to decorate the function. In practice, this means that when the print number function is called, the decorator is first called, to which the object of the print number function, including all parameters, is passed. The first example only demonstrates the mechanism of calling decorators. The decorator will notify us that it has started. Then the function that was passed as a parameter is returned without any change. This is an important line of code. At this point, the decorator function returns an object that will be executed when the decorated function is called. The second example will be a bit more complicated. First, we define a simple function print values, which we can pass any number of parameters. The construction of this function should no longer surprise us. Once we run it and pass 5 arguments, we get the expected output. Now we will create a decorator for this function. Let's run the code and see what actually happened. We have created a new replacement function in the decorator. It receives all the arguments that the original decorated function print values received. It calculates how many parameters were passed, prints the information, and executes the code of the decorated function that was passed to the decorator as a parameter. Of course, we have to give her the original arguments as well. The object of the newly created replacement function is then returned by the decorator and executed from the original code location. In this way, we can modify the behavior of any already created function. So that's all for today's episode. We learned how to create our own functions and updated our knowledge of string data objects. In the next part, we will show how to import some modules that extend the capabilities of the Python language. We will also learn to work with data objects that can store date and time. If you like the Python series for beginners, don't forget to subscribe, and I'd appreciate a like too. I look forward to seeing you in the next episode.